Okay, so this is joint work with my PhD student Menqi Liu and two postdoc Hao Chen and Manqi Yong and Joan Kim. So today I'm going to talk about a real-time system and how to prove temporal oscillation among different partitions of a real-time system. So real-time systems are pervasive. There's robots, drones, self-driving car. And when you look at the software components installed on these different systems, you have actually flight controller, you have a visual recognition module, navigations, and the payload handling. And they could come from different vendors. And furthermore, the vendor, you might see some accidental interaction across these different collection of codes from different vendors, right? So this integration opens the door to security vulnerability through this kind of a real-time scheduling. So what I'm going to show you today is a new language abstraction called braided virtual timeline, which is used to do the formal reasoning and the verification of a particular kind of a dynamic priority scheduler. And on top of this, we present a fully verified real-time operating system kernel built on top of 30 cores using this style of budgeting enforcing EDF partitions. And we have a mechanized proof of temporal oscillation between partitions, and the code and the proof are available. So first, to give you a high-level overview of what is the problem of temporal oscillation. Everybody knows what is a spatial oscillation, right? If you have a memory, you try to divide them into different parts, and you don't let different process use each other's memory. You can use virtual memory. That gives you the spatial oscillation. Time resource can also be distributed across different real-time modules and using real-time scheduling. So in our talk, we will use the notion of a task to represent things like process and so on. So real-time task, we will have a budget E, which is the amount of time you want it to run in every period P. And we also have a notion of a partition, which is really a group of tasks running within each partition. And this whole partition have a budget capital C and a period T. So that's the terminology we are going to use. And if you talk about task level real-time scheduling, you can think about things like real-time periodic scheduling. So we have a period P, the CPU time simply divided into units of time slots, period P, which is a task repeats execution during each period, and the budget E, a task executes for at most E time slots during each period. So this example of a task with the E3, P5, you can see in the first P5, you execute these 3 units. In the second 5, you execute those 3 units. So that's a valid schedule of the task. And then you can have a hierarchical scheduling, which is to divide the CPU time among different partitions. And then partitions time slots is further divided by among the tasks. So on the left side, we have 2 partitions, right? We have a pi 0 and a partition 0 and a partition 1. And on the, you can see the red ones for red partition, the blue ones for blue partition. And if you look into the red partition, you might be scheduling one task in tau 0, it's 1/6, so it has to run between 0 to 6, and another instance of tau 0 from 6 to 12, and so on. So what's tricky is if you are not careful, you might get a different kind of a schedule. So for example, in the case you are not running any blue partition pi 1, you will have tau 1 and tau 0 flipped. And if you have a blue partition running, you will see these blue partitions 2, 4 that used up this slot. So you have to run tau 0 before tau 1. But if there's no blue partition, tau 1 and tau 0 are flipped. So if you do that, you might be able to learn the knowledge about pi 1 by just looking at the local schedule of this pi 0. So that's the kind of information flow vulnerability we want to prevent. So the technique that we developed to verify temporal oscillation in the past focuses on fixed priority scheduler, more like rate monotonic scheduling. And we use the idea called the static virtual timeline. It's published in POPO 2020. So the idea of a virtual timeline is the kind of a map from the actual physical real-time t. So you have this pi I t means the amount of available time of a partition I within global time 0 to t with t instant not included. And so the idea is if you have a 3 partition, 1030, 1040, 2050, so if you use a fixed priority scheduling, then the one with the lowest, smallest period gets scheduled first. So the virtual timeline of, for this 0 is basically all times available because this is the moment this has the highest priority. And if you use up this particular partition at the next partition, partition 1, then the only available time are those white space because the purple one has already been used by partition 0. And then if you go to pi 2, you will realize, okay, so these things are already used by partition 1 and 0, so this is the only available thing. So the virtual timeline can be actually depicted as these different lines. The red line shows what's available for partition 0, green means partition 1, blue means partition 2, and they don't overlap. So this is what we developed in the past. So if you actually want to use a partition scheduler, ideally you want an EDF scheduler because EDF scheduler has this compositionality property. That is, you don't need to know what other partition period or other tasks period is. You only care about the utilization. So if your period is Ti and Ci, you only need to calculate Ci divided by Ti, which is the utilization. And you just calculate if it uses 20% of the CPU, then the other 80 can be used in any combination. But if you use a fixed priority scheduling, it's actually, the schedulability is much more tricky, and you will have to, it depends on what set of task you have, what combination of a period you have. So we don't want to use the fixed priority scheduling, we want to use EDF scheduling. So the EDF scheduling actually brings this dynamic priority, schedule. So just to look at an example, you have two partition. Partition 0 is 2.5, partition 1 is 4.9. So initially, 5 is the earliest deadline. So we have to execute partition 0. And then at the moment 2, we execute partition 1 for 3 units. Because now at the moment 5, the partition 0 arrive again, but you still execute partition 1 because the deadline is 9, that one's deadline is 10. And so you continue this process. And at instant 9, you execute partition 1 because it has a shorter deadline, so 18. And then you at 10, you execute the partition 0 again. So you get the idea how the schedule, the priority changes among partition at the runtime. So the problem, of course, is the static virtual timeline technique we used before no longer work, and it's not obvious. In fact, this virtual timeline changes at the dynamic times, and their timeline will overlap. So this particular paper basically tried to show you that we can make this virtual timeline work even though there's a dynamic priority scheduling, and we use EDF partitions, and by impose the limitation that every task running inside each partition, if their period, this task period is the multiple of the partition period, then we have the proper temporal oscillation among these different partitions. So that's basically the high level point. And we want to, so what I'm going to talk about next is just to show you actually how we actually formally prove this. So the overview of the proof start with a very concrete scheduler. We have the partition scheduler and partition local scheduler. So inside each partition, we have a local scheduler. And we are going to show through a sequence of refinement that it's a refine some abstract scheduler, EDF partition scheduler. And from that, we can deduce that the particular set of tasks is actually indeed schedulable. And from that, we can actually show that given particular local scheduler, they are still support temporal oscillations. So let me show you first the real C code of what a partition scheduler look like. So this is basically a C code written for the EDF scheduler. We have actually T represents the global time tick, N is the number of partition, TI is just a pre-specified period of partition I, and CI is a pre-specified budget of partition I. And QI represents the remaining budget of partition I. So the first loop simply initialize at moment t. If this t moment divisible by ti, then you will refill the budget. This is the amount of work CI you need to do in the next capital TI period. And then once you initialize this, you try to find the earliest deadline. You start with the PID n because we're only going through 0 to n minus 1 partitions. And if this remaining budget, if the remaining budget for partition I is larger than 0, if it's equal to 0, then we ignore it because nothing needs to run. But if it's larger than 0, we try to calculate what's the deadline of this partition I by doing this divisible thing, and then see if it's less than the minimum deadline. If it's less than, we set the minimum deadline. So at the end of this loop, you will get a process ID that's less than n. That means there's still some partition needed to run. So you just decrement by 1. You return that's the partition are actually running. So this is a real code, the C code that actually run to support this partition scheduler. So to just move forward towards a somewhat more abstract version of the partition scheduler, we introduce a pre-queue table, which is just a mapping from priority level, P to the partition ID at time instant T. So imagine this is just a ghost state. You already calculated logically at any moment T. And we simply replace the loop, calculating the earliest deadline with this, ghost function pre-queue table. And now at any moment, you just basically start from priority 0, try to find whether there's any partition available at that moment. If there is, and it still has a remaining budget to run, then we will pick that partition to run and break out of the loop and return that. Otherwise, we, just keep looking for the next partition to run. So that refinement is actually reasonably easy to prove. Next, you introduce the real-time, the virtual timeline. So we use this lowercase pi I, little pi I, to represent the virtual timeline for partition I, which is a mapping from global time to the accumulative available time. That is the accumulated available time available to this particular partition I. And what's cool is that now we are actually not doing the static calculation of this virtual timeline, because this virtual timeline is being updated at every moment, at every instant T. Again, this is a ghost state. It's simply used for our verification. So what this loop shows is simply says we are updating this virtual timeline based on at any moment, and if for the priority I partition, and if we are going to update the virtual timeline properly, and if by adding 1 to the pi I t minus 1, otherwise it does not change. And if there's this condition simply shows if this partition still haven't finished all of its budget, then you clearly need to run it once more. You will assign this I to PID, and then this is the PID that's going to run. Otherwise, this is not going to, this already run enough, and you will simply do nothing. And if you don't get chosen, it will update interference vector, which is used in the proof. So you can actually show that this particular abstract scheduler also can be refined by the previous version of the abstract partition scheduler. And so, and from this abstract scheduler, you can actually directly reasoning about the schedulability. In fact, the high-level idea of the schedulability proof is just to say at that moment, the virtual time will tell you how much available time you have at the moment k plus 1 multiplied ti, and what's the available time at k ti, and if the difference is larger than the budget, then it shows it's schedulable. At the very high level, I can use a concrete example to show you how do we actually, if I give you 3 partitions, 1040, 1030, and 2050, clearly their utilization, when you add them together, it's less than 100%. So clearly they are schedulable. But how do we actually prove it's schedulable? Well, so the high-level idea is you first try to lift every of these period uniformly to their least common multiple. So least common multiple of 3 period is 600. So you just lift each of these by the factor of LCM divided by TI, which basically turns these 3 partitions into 150, 600, 200, 600, 240, 600. Because they have the same period now, clearly it's schedulable, because if you have the same period, it's less than 100%, it's schedulable. So this schedulable can be easily derived. And then you try to enlarge every partition by the TI divided by greatest common divisor. Greatest common divisor of 3 is of these 3 periods is 10. And so, so in the case of 200, 600, we are going to enlarge it by 3, because TI is 600 divided by 10. It's lifted by 60. Sorry, it's a TI, which is 30 divided by 10. It's 3. And so you enlarge one partition here, then you enlarge another partition here, then you enlarge another partition. So each of these enlarge step always enlarges the one that leads to a largest period. So these are the enlarge operation. Once you enlarge them all the way to this, then you can shrink all of them by LCM divided by GCD. In this case, is 60. It will go back to the original set of parameters for these 3 partitions. So through this proof, you need these 2 operations. One is enlarging one partition. And the reason why enlarging one partition is always maintains schedulability is because when you're enlarging a partition, you kind of delay one of the partition's deadline to the future. So the interference, you will basically make other task easier to schedule. And so the total interference from other partition does not increase. And so therefore you can show this is still schedulable. And once you actually enlarge all the partition, and so that all the period and all the budget are all divisible by k, you can actually prove their schedule will always be scheduled in a way where all these consecutive slots are also divisible by k, and so you can do the shrink by k operation to get to the real schedule you otherwise would get. So this is how the schedulability proof was actually done. And let me briefly comment on how we actually verify the temporal oscillation. So now we actually get into the local scheduler running inside each partition. So the local scheduler, you could use any kind of local scheduler. Remember, we have the requirement that all the tasks running inside each partition, their period has to be a multiple of the partition period. So this is one example of the local scheduler used inside a partition. It basically uses a fixed priority scheduler. And the first part is just initializing the remaining budget for every task. And again, it's just, if T divisible by PJ, and it will be initialized to EJ. And then you use a fixed priority scheduler basically just to go through each of these tasks. Now, this local scheduler is not necessarily obviously temporarily isolated from other because it relies on the global time T. So, however, you can show this local scheduler is a refinement of the next scheduler, which is an oblivious local scheduler, where if you just replace the LT with replace the T with the local time, which is the local time experienced by the enclosing partition, and the LPJ, which is the logic period, equals to this period J, PJ multiplied by the enclosing partition's utilization budget. So, for example, if I actually have a partition 2.5, and inside I have a task 2.15, then the logic period is really 6, because that's actually in time 15, this partition only gets 6 units. So LP should be 6. And then you basically, LT counts how much logic time you have used within this 6. And you will increment this logic time LT. So if you do this, you can see that the local scheduler does not rely on the global time, and it's oblivious local scheduler. And indeed, through this, we can verify that the schedule of every partition task inside each partition has a temporal oscillation properties. So you could show the simulation diagram, the details in the paper, how the logic time is related to the global time, and so on. So I'm not going to go through that detail. So remember, the key idea is we are trying to avoid this problem, information flow vulnerability coming if the flipping problem. We want to avoid that these schedules do not flip. And so indeed we implemented our verified scheduler, and we run multiple on many test cases. So I'm just showing you one particular examples where we have a partition 4, which contains 4 subtasks, tau 4.1, tau 4.4, and at the inside this figure A, it's running the solo partition, and we are basically seeing that the period of the partition is 50, and inside each of these partition, you have these different tasks: the blue one, the gray one, blue one, orange one, and the purple ones. And you can see they are, without any other partition running, we get a trace looking like this. Each of these tasks have a period divisible by 50. So the next figure B shows what happens if there's another partition running. So now you can see that the actual time this partition gets executed is no longer always at the beginning of the period, like 50. Instead, it is a little bit beyond 50 boundary, right? And so on. And now the figure C shows the case where you have 3 other partitions running. So that would further disrupt the schedule of this partition 4, right? And so you see that originally things are running consecutively. Now actually they are divided at a different time. So what temporal oscillation says is regardless how many other partitions run, within the logic time space, when you look at how these different partitions and look at how these tasks are run or scheduled, they don't change. So it's always gray followed by blue, followed by orange, and followed by, they always follow the same task, even though they might be divided in some cases. and they still basically follow the exactly same shape. So if you concatenate these things together, they will look exactly same shape, which means you are not getting influenced by how many other partitions are running in your system. So, so this is all formally verified. The scheduler is formally verified inside the COC. So we basically formalize the dynamic virtual time map, and we have the schedulability proof. We does not rely on any external schedulability module to prove that the thing is schedulable. Instead, everything is included. Functional correctness proof for the scheduler. So these are just showing how many lines of code we actually have to write to prove various set of properties. You can look at the paper for detail. So to summarize, we developed this generalized notion of a virtual timeline, which we call the braided virtual timeline. It's a cool abstraction that allows us to verify dynamic priority scheduler. We really believe this EDF scheduling is very cool for the utilization. So we have built a verified real-time OS using this partition scheduler, and this OS is running on small self-driving car prototype, which it's part of our DARPA project, and we have the mechanized proof of temporal oscillation. Okay, that's it. Questions?
No questions, then let's.
Okay.